Okay, here we are in our last module 6. We have 2 short lectures to get through, a couple of quizzes that go with those, and of course there's a larger assignment that covers a little bit of residency material in this for those who are going to go that route. So we have a couple of topics. Our first one is going to be parametric programming. It's related to the work we did in residency, and it's really just an extension of sensitivity analysis that I want to make sure everyone has a pretty good handle on. So if we track backwards to Module 5, we were building out just a classic simulation model that depended on demand, and we were looking at profitability adjustments as prices change, and of course the filter, the sort of key ingredient, was the demand curve. There were some other things, and some other things we would have uncertainty about, and certainly we would want to be testing all of those sort of sources of uncertainty. But the that one of the key pieces was, what does this demand curve look like? So here's the quantity sold impacted by the price, and that how the price adjustment impacted the quantity sold depended on the elasticity. And we said it was just a slide from Module 5. I said it was the classic version of a parameter, this fixed coefficient that tells you the relationship between two things, one a choice variable and another being a response or a metric. And then of course the alternative to just using the elasticity would be the demand slope and the intercept. So if we were to look for a definition, then that would be good enough, right? We would say that parameter governs or clarifies the relationship between quantity sold and price. It's either going to be the elasticity version, percentage change in quantity divided by the percentage change in price, or the level version here, where you end up with a quantity is equal to an intercept plus the slope being the controlling or the governing parameter that tells you in a unit change in price gives you how much change in quantity. But we should ask ourselves, we take demand curves and we estimate them, and we say that this is a good representation of demand, or maybe you add in some other prices and you do some statistics, but where does the demand curve come from? And in fact, that's a good problem for us to consider here, because it comes from an optimization problem, much like the problems we've been working through in this class. So let's take an example. Let Q and T be two different consumer goods, and they have prices P and R respectively. So we pay P, 1 unit of Q costs P, 1 unit of T costs R. And then finally, or additionally, let M be the income level that we have. And then, I don't know how far you have to go back to think to your microeconomics where you had utility functions, but that is what this is based on. It says maximize the utility, where utility is some definition. This U with parentheses here just says that there's every combination of Q and T, the two consumer goods, will give you an outcome that can be measured in utility. And utility is something we want to make large. Okay, so this is the cornerstone of consumer economics, is utility, something we'll never measure. So keep that in mind when you're working through these problems. The other side of the problem, the subject to or the constraint, is something we'll always be able to measure, the income level. And so the idea being, having money itself is worthless, and so it's really the fact that we want to spend it on things to convert into utility, into satisfaction or happiness or whatever definition you want to use for utility. And so the total expenditure will always be the price times the quantity plus this price times this quantity. Add these two things together, they have to be equal to our budget, assuming we spend everything. This is the disposable budget or disposable spending allowance. So we spend it all to get the most utility. And so one of the questions we could ask, if we treated this as a quantitative problem to solve over and over, If you tell me the constant level of R, right, the price of good T stays fixed, and the income I have stays fixed, then this is a problem I could solve repeatedly considering different values of P over and over. Okay, so start with a level of 0 and say I solved and it gave me 20 being the quantity I want. Solve again with the price is equal to 1, and now I only want 15. Solve when the price of good Q is 2 and I only want 10. And so that's what we would be doing. So we would be solving to get the Q and P quantity and price pairs that actually form the demand curve. And that's what, I mean, this is what PhD economists sit around doing and thinking about sort of different specifications of demand curves. So it's a simplified example, but these are exactly the outcomes they'd be looking for. And so parametric programming then is really just trying to summarize one piece of this complicated optimization problem here. Maximize utility subject to the budget spending, budget allocation on these two goods. And parametric programming just says, okay, let's vary one parameter, hold everything else constant, and see what the outcomes are. Then you get this summary demand curve that you could draw and say when Q, the intercept of this would be 20 and the slope would be -5, and so it would be 20 minus 5. And that would be the linear demand curve that you would proffer out of this data. And so with that in mind, whether we actually build the model, the utility model, or whatever model behind our demand curve, or we just take it as given like we did in that Simon Pye's spreadsheet model here, for that demand function to be meaningful, it must represent the solution to an underlying optimization problem, right? It must be that this demand curve, this relationship, -4,000, is exactly what you would find if you could go back and solve the utility problem over and over and say, I want to now increase the price of pies by X amount. How much does Q adjust? Right? If that isn't the underlying sort of driver here, then we don't have the economic response in this model correct. And so that's really the essence, the definition of parametric programming. It can be done for demand or other functions. So traditionally, when we want to know what demand is, we gather data historically. We go out and collect what has this market produced in terms of a market price over time, what has been sold in this market as quantity. If we had good firm data, we could say what price are we facing as a firm or trying to charge as a firm, and what have sales been. And we could use statistics to try to fit a demand function through the points, through the quantity and price information we have. But even there, the demand function you write, the underlying assumption, the idea that slope needs to be negative comes from the idea that choices made by purchasers should be because they are out there making their best choices. If prices go up, we expect the aggregate of consumers in a market to respond, the average consumer in a market to respond, and we should be able to pick that up in historical data. So even when we're just doing statistics and not an underlying optimization model, the specification, the type of thing we're trying to estimate has to have behind it an underlying choice problem that is governed by optimization. Okay, so why are we doing this parametric programming thing? If the best choice is to go out and get historical data, well, it may not be the best choice. What if we have an isolated firm and we know quite a bit about the firm and we know about their access to some local market, but we don't have a long history of data, or we don't have what we think would be the sort of right period of data because things are about to change? Well, we could specify an optimization model that we think sort of describes the new setting for sellers in the market and for buyers in the market, and we could go through there and simulate or build out these different price changes parametrically and solve it and get a solution. Okay, and so that's one option, and there's just lots of cases where our firm is too idiosyncratic to believe that we face the market demand curve, because the market demand curve, you may have learned, is the summation of everyone in the market. It is an average, and we may be very non-average, and we also may have competing interests in the firm that cause our optimum to adjust much more steeply. We might need to respond with a much steeper firm level demand curve because of some constraints in the firm. And the only way to capture that would be to build this alternative decision model for the firm and do a parametric programming approach to get what our demand curve looks like. And of course that leads to the main advantage. It gives you a way of embedding an optimization model in a more complicated or complex simulation. So that Simon Pye's example, it has quite a few things on the unit cost side, especially if you were trying to move into uncertainty and use some of the sort of at-risk simulation techniques you got in Quantitative Modeling 1 or Quantitative Methods Semester 1, rather than just taking a sort of bold and maybe a proxy solution of average data and saying this is the best representation we're going to get. We could actually build our own optimization model that tries to reflect the sort of idiosyncrasies that matter, and we would have that embedded. So a classic example would be going all the way back to Module 3, take our animal diet. Okay, so we solved this, and we were using this to demonstrate a couple of things. What happens as you get more choices in the option here, and what does it take to compete with this superfeed option, right? I believe that was what we did. And we had this ration over here set exactly to meet the superfeed requirements to see how much of these four goods it takes to overcome that. Well, one of the things we might do with a model like this would be to just start changing the price of soybeans and get what we would call a bean demand function for this firm. Right? So we would keep solving this over different levels of the price for beans, different assumptions, and then just see what the optimization problem told us was the correct choice, the cost minimizing choice. And that would give us an internal demand curve, demand representation that's optimal for our animal feeding firm. That would give us the right price response that we should embed in any model that's representative of our firm, even if we're not solving for the ration over and over. And we may be very different than the market as a whole in the way we want to respond. So if you go back to that beans model, and it has four choices in it, you get this solution, I believe. And so what you can do is start from the solution, and we see that if the price of beans is 94, then the solution value is 0.78. Okay, so that gives us, if we're trying to extrapolate our own demand response for beans in our firm, then the initial point we would work from would be P equals 94, Q equals 0.78. And then we want to work around that with increasing prices and decreasing prices. And it turns out we're given the next step, right? So we know that this solution here doesn't change until you either go bean price approximately 40 larger or approximately 15 smaller. Okay, so these are the allowable increase and decrease that say if this value, this objective coefficient, goes up by more than this or falls by more than this, then this solution value will change. But in between plus 40 and minus 15 approximately, that value will be stuck at 0.78. And so we just need to run new experiments in our optimization model for plus 40 to the bean price right here and minus 15, and we would get new points on the demand curve. So let me... Okay, I have my spreadsheet open now. You can see I've already been through this problem and solved it, but let's go back to the beginning. And so this is Lab 1D is the name of this. It's the last lab experiment we did in that Module 3, I guess. And so I could go to Data, Solver, and everything is set up there, and click Solve, and you get that 0.78, that initial solution. And then if I click on the sensitivity report, it'll tell me that plus 40 minus 15. I'm not going to do it. I already have the sensitivity report open here. And so we can see it now. So at 94 plus 40 minus 15, and so I could come back over here and let's say I wanted to do the upside, the plus 40. I would just change this to 134, go to data, go to solver, click solve. That's the only thing I'm changing. Whoops, what did I do? Oh, yeah, okay, and so when you go up to that, the solution changes and beans goes from 0.78 down to 0. Okay, and then if we lowered it down to 79, solve it again, and you see it goes up to 1.77. Then you could open the sensitivity report again. I've already got that one. And we could check our sensitivity report, and now we only need to check the allowable decrease. Let me blow that up again. Okay, so the current setup is the objective coefficient of the price for beans is 79. The allowable increase doesn't matter. We've already been on the upside of this. And so the allowable decrease, 71.66. We could go down to a very small value. You can see I calculated it here. So something around the value of 7 before we get a solution that changes from 1.77. And in fact, I've already calculated that down here. So I've got all the bean. I've got 4 values for the bean price, 4 values for the bean quantity, and then I plotted them here as bean price versus bean quantity. And those were the things I had in mind. And that's the values that I had in the final form here of the bean demand. Okay, so at a price that's too high, we want 0. As the price falls, we expand the quantity demanded. So this graph shows all the non-negative outcomes that come from our optimization model. We're holding everything else constant. So that means the non-bean prices and the right-hand side values. So the location of this, everything in this curve, is dependent on us having the best set values for the rest of our optimization model. And so we'd have to ask ourselves, is it a good representation? Is it correct to take some interpretation of these 4 points and say that is our demand function for the firm? And you could do lots of things. I've allowed it to connect the 4 points with straight lines, and you could interpolate those and give it different slopes for each of those changes, saying, well, some mix, some partial response could happen in between here, right? If you wanted to think about sort of a bigger options model, one that had lots more choices than the representation we have. But technically the model is saying once the price goes a little bit below 140, jump down here and start consuming this quantity. It's saying once the price goes a little bit above this, you want to go straight to 0. Okay, so the quantity jumps over here and then climbs up to here. And so it would be more like having a stair-step function where these were connected by right angles. I'm having a hard time tracking with my mouse, but that's the sort of true representation. But data points out in the world have error too, and so we've built something here that's linear, and we might believe could legitimately be connected by linear segments. We could also think about what would the best curve function look like, or the best fit function through these 4 points. So if we were really into having one straight line that represented all of our demand so that we could just use a demand slope, then a best fitting demand line through these 4 points would be much more representative of our firm on average than using market data. Okay, and so there you go. If you're building an optimization model, one of the problems that you run into is the models can get big because the problem you're dealing with may be big. But you may have one small corner of your analysis that has an optimization model, and you wish there was a way to embed it in the larger model without having to, every time you adjusted assumptions, go into solver and resolve the optimization model. Well, this is a way to get all of these sort of average or response behavior out of an optimization model over into a model like the Simon Paz model that really just wants to work around what is the slope, what is the average response across the firm, right? Across all decisions. Yeah, and so that's really the topic there, and you'll have a quiz where you get to play with one of those. Other uses of parametric programming, really if you have an optimization model that's core to your analysis, it may be the best way to represent sensitivity information. What is our best response picture when the market price, right, especially if we're price taking as a firm, how do we respond when the market price moves? It could be a price of something we're selling or a price on something we're buying, right? How does the soybean price, if I'm a feeder, how does the soybean price change the internal demand here, not just of beans, but of all the other goods, all the other feed items we want, right? It was a classic problem 10 years ago that I published papers on when corn ethanol prices caused corn prices to go too high to feed in rations. And so we did lots of work on this where we used parametric programming out of diet models to try to build out simulations of the impact in the across sort of agricultural industry, but really focused on sort of substitution possibilities for corn and feed rations. And here's what you will do in the quiz. So for input demand, how would you compare if you wanted to make adjustments to the right-hand side? Well, think about this. If you started changing the protein requirements on the right-hand side of a ration model, then how do the protein shadow prices adjust? And so that's one thing you can look at. Risk-efficient frontiers trade-off curves. So in residency, we looked at that, sort of the mean variance frontier. That was repeatedly solving for the lowest variance at different expected returns, right? So you put together a minimum return requirement, solve the model for the lowest variance, put together a new minimum return requirement at a higher value, and solve for a new variance, right? And then we expect that to go up and give us a picture of the mean variance relationship facing the firm as a decision entity. Other risk measures, and that's where we'll cover in our last short lecture here.